Welcome to this set of lectures that I've prepared on the finite element method. These presentations or videos will cover both theory and a set of tutorials that I've developed which use open source code. I've tried to link together the theory with these tutorials. And in this preamble, I would like to just give you some ideas on the chapters that are included in the book on the theory, and also the tutorials that I've developed. And finally, I'd also like to give some ideas on why I've chosen these particular codes that are used here. The book's split into two parts. Chapters 1 through 6 cover basic theory. Chapter 7 is covering modeling methods, and then following this there's a part 2 which covers 14 different tutorials. On the next slide I'll give you some ideas about these different tutorials. Each video that I shall be producing will cover one chapter, and I try to split it into different parts since the videos can be a bit long, at least some of them are. I start off with video 1 on chapter 1, covers basics of the finite element method, a kind of overview, formulations that are used to compute stiffness. For this I concentrate on the 1D bar element, boundary conditions, application of loads, assembly of element stiffnesses, essential basics of the method. Chapter 2 is dedicated to stiffness matrices and integration methods to compute the stiffness matrices. There are 3 techniques I go through there which cover basically the historical development of the method. I focus mostly on continuum elements, but in the book itself this chapter does include beam, plate and also shell elements. Chapter 3 is dedicated to nonlinear, dynamic and eigenvalue analysis. So essentially the algorithms, the techniques that are used to perform the different analyses. Chapter 4 is fairly short, just gives an overview on loads, boundary conditions, and a fairly short section on contact, which can be treatment of contact between different bodies. This can be important in some types of analysis. For chapter 5, it's solely focused on heat transfer and related field problems. The tutorials themselves do use a variety of different materials, so I thought it would be useful to have a chapter dedicated to material constitutive laws. This could be a book in its own right, so I've only concentrated on 3 materials. Elasticity for isotropic and orthotropic materials, so the sort of material laws that you would use in composites analysis, for example. I then go on to hyperelasticity, which you would use for rubbers and polymers, and finally plasticity laws. Chapter 7 is focused on the different softwares that I've used and why I've used them. I also take the opportunity to say something about the sort of techniques you should be thinking of for modeling. And then finally I go on to the tutorials themselves, which I explain better in the next slide. These then are the 14 tutorials that I work through in the book. The first is a 3D solid analysis. For this I use a so-called unit cell of a composite and consider both isotropic and orthotropic elasticity. The second is a 2D shell analysis, also of a small component, considering both elasticity and orthotropic, again composites. But it also looks here at the bending behavior of shell elements. The third is a nonlinear analysis involving large deformations and material plasticity. For this example I use an adhesive bonded lap joint. Then I move on to fatigue and cycle life analysis. This is quite an interesting study of the failure modeling of a bike part. It ties together the way you would do a linear elastic analysis to predict peak stresses, and how these peak stresses can be used together with fatigue curves of a material in order to estimate how many cycles it would take, how many load cycles it would take before the part would break. I do include some theory there, so it's interesting for anyone who wants to get an overview of fatigue analysis with finite element codes. Tutorial 5 is a thermoelastic study of two components. The first is a bimetallic strip. It's a classical problem where you have two materials with different thermal conductivity, and it investigates the analysis of thermal loading in order to deform the bimetallic strip. And the last analysis included there is the failure modeling of a cup which is heated, suddenly heated, creates thermal stresses and material failure. Next, in tutorial 6 is a steady state fluid flow analysis through porous media. Tutorials 7 and 8 move on to linear eigenvalue analysis, first for frequency analysis and then for buckling analysis. For the frequency analysis, I use a tuning fork. This is a fairly standard example, and it's quite an interesting example because it shows one of the advantages of FreeCAD, that if you build the model based on the CAD geometry, you can easily change this, for example, the length of the tuning fork arms, and very quickly do a new analysis to predict a new frequency. In each of these two eigenvalue problems, I do also look at other nonlinear analyses using nonlinear finite element techniques. Tutorial 9 is a transient dynamic analysis which investigates the way in which heat flows through a particular structure. So this is a time-dependent problem. In tutorial 10, it investigates explicit finite element methods. The CalculiX code that I use for all of these softwares, and I will be explaining a little later, does have explicit finite element capabilities, but I was never very successful with these. So this particular tutorial programs a simple spring element in a FreeMAT code, which is similar to MATLAB. And we investigate different effects like different loading, contact, damping, and different time step used in the explicit algorithm in order to have stable and unstable analysis. Tutorial 11 is a little structure. It's a seal with metal plates, and it involves both contact, hyperelastic material behavior. It's analyzed as a dynamic transient problem involving both material contact between the plates and the seal, the rubber seal, and heat transfer in the contact. Tutorial 12 is a flow problem through a hydraulic pipe network. And then in tutorial 13 and 14, I move on to computational fluid dynamics. This is rather a separate topic, but I thought it would be interesting to include because a popular open source CFD code is OpenFOAM. This is also integrated in the CAD program FreeCAD. And in tutorial 13, we first look at programming of a simple CFD code taken from a reference. And then in tutorial 14, I move on to analysis using OpenFOAM within FreeCAD for different pipe systems and also flow over a aerofoil. So it's a bit of a wrap up on the different tutorials. And just to emphasize again, I try to tie each of these to the theory presented in the first part of the book. If you are interested to look at the different codes that are available, there are some nice links there. First of all, for CFD, CAD codes, and then for finite element codes. And if you look through there, there are a few, very few open source codes. Salome is one open source CAD code, and the other one really is FreeCAD. I'll go through these in a second. On the FE codes, there are many more, but really, again, there are two that are quite strong, I would say, and that would be CalculiX and Code Aster, which I will also mention in a moment. I looked at both of these options. You can either use really FreeCAD with CalculiX integrated, or you can use Salome with Code Aster. They are both good options, but I decided in the end that FreeCAD with CalculiX would be the most suitable for what I was aiming to do with this particular book. There is a website given there for each of these codes if you would like further information. I think the strongest points for FreeCAD with CalculiX is that it's very well integrated, meaning CalculiX is so easy to use within FreeCAD. It has excellent meshing possibilities. You can mesh the structure at the CAD level, which means that if you want to change some dimensions of your model, it is so easy to do that, and the structure will be automatically remeshed, and the analysis is very straightforward. The post-processing in FreeCAD of the CalculiX results is not great, but I think it's perfectly good enough for these sort of teaching purposes. And there are other possibilities. You can use ParaView, which is an open source post-processor, and CalculiX does also have its own post-processor, which is again not great, but quite reasonable. There are other codes available to be used with FreeCAD. One of these is OpenFOAM, but there are some other ones which I will go through in the lectures. Regarding CalculiX, I think that it had a number of advantages. It has a wide range of possibilities, so it analyzes linear, nonlinear, dynamic, eigenvalue problems. There's a fairly large library of material laws. I think one of the best advantages perhaps is that the input format is based on Abaqus. So any student using this particular code will also gain the advantage that he learns something about Abaqus, indirectly learns something about Abaqus. There is reasonable documentation, and it does also, as I just mentioned, have its own post-processor if necessary to be used. I did try some analysis with the options Salome and Code Aster. I found it a bit more, quite a bit more, how shall I say, time consuming to build models. And I think that was one of the main reasons I didn't use it. People have also commented that you have to have some knowledge of French in order to use it, since the code is developed, at least Code Aster, the finite element code, is developed by the French nuclear industry and is now open source. So the documentation does tend to be sort of mixture of English mixed with a bit of French. This slide and the next slide give you some information, some links on the location to download FreeCAD, and some links where you can get further information. Perhaps you're interested to have a look at these before you embark on the other lectures that I've prepared. If you do download FreeCAD, you will find that CalculiX is already integrated within FreeCAD. You can obtain FreeCAD both on Linux system or Windows. I've used Windows for all of the tutorials that I've done. I found it worked very well, very reliable actually. So the link for the download is given here, and as I say, these are links where you can get more information, and you will find an enormous number of videos, actually YouTube videos on these softwares that you could run through if you are interested. Here are the links for the CalculiX website. This is the main link where you can get documentation and examples. There are also further useful links here where you can get additional information. Now, there are some limitations. CalculiX, for example, has a large library of materials. It also has a large library of element types. And at the moment, FreeCAD does not support all of these. But I think for the for teaching purposes, there's more than enough, and the tutorials that I've prepared do kind of demonstrate the variety of problems that you can analyze with the standard versions of FreeCAD and CalculiX. Again, CalculiX is available with Linux or with Windows, but I have used always the Windows version, which is integrated within the Windows version of FreeCAD that I used. If you want some other books, these are 4 that I tend to use. They are very detailed. That's not been my aim here. I've tried to produce a book which is a textbook for teaching purposes. These tend to be more reference books these days. They cover almost all topics on finite element in some way. The classic book is by Zinkovich here. He wrote the first finite element book, and it's gone through some modernization, shall we say, over the years and improvements. This, I think, the one I'm showing there, I think, is the last version. Similarly, this book by Robert Cook and co-workers, I think the first version was in the 1980s, and it's been continually improved and updated, and I think what I'm showing there is the last version of it. Another classic book on the subject is by Barter, given here. I also find this book here very good, by Rao. The version I have is earlier, and he doesn't go through nonlinear analysis. I do not know if this latest version does, but this is, I do find this quite a good book. But there are many other books, as I say, you will find available on the web. And just to summarize my motivation for doing this particular book, I was aiming to produce a textbook on what I regard as essential finite element theory. This is based on teaching I've done over the last 20 years. It is mainly for teaching purposes. I'm not really trying to do a reference book of any type. But I think the main novelty perhaps of the book is the set of tutorials, the use of open source software and the coupling of this to the theory. I know that there are lots of softwares available from commercial companies, but they usually have some kind of restriction or some kind of payments. And in this case, I just wanted to use open source software as far as possible. So basically anyone can download this and use it at any time. So I hope that gives a quick introduction to my aims of this book and the contents of the book. If you are interested, please feel free to go through the lectures, and if you find those useful, perhaps you'll be interested to get hold of the book. It is available, as I say, on Amazon. It's a self-publishing book. I preferred to go that route so as I had as much control as possible on the book. But if you do, I hope you will find it useful.